So, the first line of defense, as always, is it undoing the chain rule? Undoing the chain rule. So, no, not really, right? So we don't have this idea of G prime F times F prime, right? So then what we've got is undoing the product rule. And your last couple examples were these arc inverse or arc trig functions in the homework of undoing the product rule. So we got to figure out what F is and what G prime is. Well, if we made G prime arctangent of 3x, well, that kind of puts us back at the original problem, right? Because we've got the first thing we have to do with G prime is do antiderivative, right? That's part of that. So it doesn't really make sense to put arctangent here because then we've got the exact problem with it. To solve it, we've got the same situation that we're actually asked to do in the first place. So then that leaves putting arctangent here at F because we know we can take the derivative of that. And then what is G prime then? 1. Okay, so that makes G, X, and F prime. It's going to be 1 over 1 plus 3x quantity squared times 3 by the chain rule, right? So there's our F prime. And so now we can say that that thing plus the integral of 3x over 1 plus 3x quantity squared dx, and that's going to equal F times G, right? F times G is x times tangent inverse 3x. So that's our basic undoing the product rule form. F times G equals the integral, which we're calling A, the answer, plus the easier one, which then becomes integral of F prime G, or 3x over 1 plus 3x squared. And so the question is that easier? So we should recognize that this is 3x over 1 plus 9x squared. Can we do that one? And how do we do that one? Undoing the chain rule, right? Because we've got this denominator or to the negative 1 here, and then we essentially have its derivative there. So we're going to solve this one by undoing the chain rule, and then we'll have it. We'll just rearrange and solve for A, right? So what is the... Wow. I don't know what happened. I guess when you're just close to the thing, it also writes, not just touching it. Okay, so this is squared. So what is this? What is this? Basically, it's 3x times 1 plus 9x squared to the minus 1. And the derivative, or the antiderivative of that is, so we're going to focus on 3x, or we're going to focus on this part to the negative 1. Focus on this part to the negative 1. And all we have to really do is just do the antiderivative of the big picture of that, right? The G prime, what's the antiderivative?
The 1 of the absolute value of 1 plus 9x squared.
It's be natural log, right? Natural log, because we got something to the minus 1. So those will come over here. I'll do this in red. First attempt. First attempt is natural log of, yes, I could put absolute values, but because it's 1 plus 9x squared, that'll always be positive. I don't really need them in this case.
Am I going to lose points for using absolute values?
No. So what he said is you don't really need them, right? It doesn't change. It still is okay if you have them. Okay? But because it's 1 plus 9x squared, don't need them. But if you have them, it's just redundant. It's not wrong. Okay? So then, what are we going to have? So when we do and so we have 3, right? From the 3 here. And then if we took the derivative of this, we'd also have what? A factor of 18, is it? We'd also have another factor of 18. So our second attempt would be, what, 3 over 18, natural log, 1 plus 9x squared. So I think this will do it. That would become 1/6. And so let's just check that. I'm going to check that. So the derivative is 1/6 times 1 over 1 plus 9x squared times 18x. And that should equal exactly what we started with here in this integral here. And it looks like it is, because that would be 18 over 6 is 3x over 1 plus 9x squared. So check. So we got the right antiderivative. And now we're ready to write what a is. What is a? A is this thing minus our answer to this integral. So it's going to be x tangent, or arctangent x minus 3x. Sorry. I lost the x in this line right here. Sorry. Thank you. So arctangent 3x minus our answer to this integral, which was our 1/6 natural log 1 plus 9x squared plus c. Questions on this example? That has a lot of, or almost includes everything we've done so far, right? So you have to do undoing the product rule, but then when you get to that easier integral is undoing the chain rule, which is the natural log. So, really good example. Hopefully you had some degree of success. But in the web work, it was 96% success. So, we'll see if it's the same on paper.
Just explain why G prime is not.
Well, so because this integral is the integral of f g prime, right? And this is our g prime f, right? So that the basic form is this, right? So we got to figure out what's f and what's g prime. Well, there's only one term, so it has to be that thing times 1. Just because there's only one thing there. And then we decided that the arctangent of 3x has to be f, because if it were g prime, then right here we'd have the same problem we're asked to do in the first place. So that forces the tangent inverse 3x to be up here at f. And we saw that with the last example on Friday with the natural log. So then we can do the derivative. So once we've decided it's undoing the product rule, then it's 1 times that thing. 1 times that thing. Other questions? Yes, please?
There's also a rule of thumb that we can use whenever we're deciding what f would be, is the Lie. It's like logs, inverse n, algebraic, trigonometric.
Oh, you have a little trick for it?
Yeah.
Okay.
So like
Email it to me. Email it to me, because I've never heard that before. Yeah, email me, and then I'll share it with the group, because I've never heard that before.
It's every time.
Okay, good. Other questions?
Are you recording?
I think so. Did I turn it on? I turned it on, didn't I?
Yeah.
Yeah. But thanks for asking. Okay, last chance. Questions on this?
1 plus x squared.
There we go. So, really important example because it includes so much of it includes like everything we've done in terms of these techniques, right? It has both techniques involved. Okay, so if it didn't go well, it's only one quiz, right? So quizzes are 5 or 10%, and it's just one of them out of all of them. So just know that when you do the web work, it's you got to make sure that you could do all those problems by hand as well. So you have to have a little self-discipline that the homework is about really learning how to do it when there could be ways around that. Okay, so I'm aware of that, and you need to be able to actually work them out by hand and show me that you can. Okay, instead of just getting the right answer on web work. Okay. Last chance for questions on this. Okay, so let's move on. And it's the next thing we're going to look at is what's called rational functions. Rational functions are one polynomial divided by another. one polynomial divided by another. So, for instance, like this. So that's one polynomial divided by another, so it's a rational function. So is this, always our first question is it undoing the chain rule? Is it undoing the chain rule? And so it's not, and just to practice, what would be one small change I could make to this? So it would be undoing the chain rule. What small change can I make to the denominator so that it would be undoing the chain rule? Yes, sir?
Make that x to the third power.
He wants x cubed plus 1 in the denominator. Absolutely, that's what would do it. And then it would be natural log of x cubed plus 1 would be our first attempt. Natural log of x cubed plus 1. But we don't have that. So we have this rational function, and since it's not undoing the chain rule, it might be undoing the product, but it's not one of our common forms for that. You know, our common forms are like x to the something times sine or cosine or e to the x, or things that involve natural logs, or these inverse trig functions. So we might be able to do it by undoing the product rule, but it's not kind of one of the common forms for it. So we're going to learn a new technique for these. And so the first thing we want to look at is if the degree of the numerator is greater than or equal to the denominator, that's what I have here, we're going to do long division. So we're going to long divide this. And so if you remember from your advanced algebra, we're going to long divide. So we're going to write out the polynomials as a long division problem. So I'm going to have x plus 1 is my dividend, right? Divisor. The dividend, no, 2x squared is the dividend, and x plus 1 is the divisor. So I'm going to do x plus 1, and I want to find out what happens when we take that into 2x squared plus 0x plus 0. So the first thing we want to do is we want to get 2x squared here. So we ask, what do we multiply x by to get 2x squared? And the 2x is going to go above the x term. So then I'm going to multiply down 2x squared plus 2x. This is just like long division that you do with numbers. And then what are we going to do? We're going to subtract. And we got the 0 that we wanted here. And then this is going to be minus 2x. And we're going to bring down the next term, just like long division. And then we're going to ask, what do we multiply x by to get minus 2x? Minus 2. So then we get minus 2x, minus 2, and we're going to subtract. And we get 0, that's what we wanted. And when we subtract minus 2, we get plus 2. And that's our remainder, right? And so then we can rewrite this integral as the quotient plus the remainder over x plus 1. So after we did that long division, we got a different form of this exact same rational function, right? So the 2x squared over x plus 1 is the same as 2x minus 2 plus 2 divided by quantity x plus 1. And now this, we're home free, right? Nothing else to do here. Except the antiderivative, which is x squared minus 2x plus 2 times natural log. Here we need the absolute values because x plus 1 could be negative. And that's easy. After we long divided, we got an easy antiderivative. Now, sometimes what will happen is you'll do this long division and you'll get something that's not so easy here. It's another rational function where n is less than d. Okay? So if we have the case where we have a rational function that's not just a straightforward antiderivative like this, and n is less than d, this requires a technique called partial fractions, and that's what this is the main crux of today, is what we call partial fractions. Now this didn't need partial fractions because it was easy. But if you have a rational function where n is less than d, and it's not just an easy one like this, then we're going to talk about something called partial fractions. Questions on this example, first of all? Are we good? Okay, so let's talk about if the degree of n is less than d, and then you have another requirement here. You need to be able to factor out the denominator. So let me give an example here. This one, 5x plus 1 divided by 2x squared minus x minus 1. So is the degree of the numerator less than the degree of the denominator? Yes. Degree of the numerator is 1. Degree of the denominator is 2. Okay? The second question, in order to use partial fractions, that numerator or that denominator needs to be able to be written as a product of factors, meaning we need to be able to factor it, or needs to come pre-factored, okay? So can we factor that denominator? If we can, then we can use this technique called partial fractions. So we try, right? So we need a minus 1 and a plus 1 to multiply, and then we need to add to negative 1. So plus 1 or not minus 1 here? So you'll see that will be plus 1 and minus 1, and that will give us the product is minus 1, and the sum of the inner and outer terms is negative x. So I think that works. Okay, so you know how when you add separate fractions, what do? First? You get a common denominator, right? And once you have that common denominator, then you can add your fractions. So what partial fractions is about is like going backwards from that process. We're starting with the result of the sum of fractions, and we're going to split it apart into the sum of fractions. So it's like the reverse process of adding or subtracting fractions. Okay, so we want to rewrite this as something over 2x plus 1 plus something over x minus 1. So do you see how if you started with this and you were adding those fractions together, that your common denominator would indeed be 2x plus 1 times x minus 1, right? That would be your common denominator. So we want to rewrite this in terms of the what's called the decomposition, right? So it's the sum. What sum of fractions is going to give us the same thing that we're trying to find? Because we could do these. These should be easy separately. Okay, so basically what we're saying is, if I were to add these two together, so a over 2x plus 1 plus b over x minus 1, I want to add those two together. So how would I do it? So the common denominator would be 2x plus 1 times x minus 1. So now, so I need to create the common denominator here. So it means I multiply top and bottom by what? X minus 1, right? Therefore, this is going to be a times x minus 1. Let me write that in there. And what am I going to multiply the top and bottom by the second fraction to get my common denominator? 2x plus 1. So I have b times 2x plus 1. So this right here is another form that is equal to that right there. Right, because this is equal to this is equal to this. And what is our goal? Our goal is to figure out what A and B are. We need to figure out what A and B are so that those are the same antiderivative. Those are the same rate function, right? We're looking at the rate function here. We want A and we're going to try to figure out what capital A and what capital B is so that we have the exact same rate function. Well, the numerators, or we got the denominators fine, right? We got that common denominator, so it's really all about the numerator here. So we're going to say that A times x minus 1 plus B times 2x plus 1 has to equal what? 5x plus 1. Okay, so we need to multiply everything out and get our x terms together and our constant terms together. So I'm going to have ax plus 2bx minus a plus b equals 5x plus 1. Did you follow that? So I just multiplied out that thing, and I'm gathering together my x terms and my constant terms. So notice I got ax plus 2bx, and I got 5x over here. So what does that mean? That means that, so this whole thing right here has to equal 5x. And this thing right here has to equal 1. Okay, so that, what I get from that is that a plus 2b has to equal 5. If ax plus 2bx equals 5x, then a plus 2b has to be 5. And then also negative a plus b has to equal 1. And so now I've got two equations, two variables, two equations and two variables of capital A and B. And so from here, any way that you have learned to solve something like that is legitimate. There's substitution, elimination, matrix method, whatever means you've learned that you're most comfortable with. So the thing that's obvious to me here is we can just add the equations and the a's go away. Do you see that? If I just add equations. So this is elimination, right? This is eliminating a. If I add my equations, a plus minus a is 0. And then I get 3b equals 6, so b equals. And if b can come down to this equation, if b equals 2, then the opposite of a equals negative 1, so it looks like does a equal 1? So from b equals 2, I can get a by looking at that one. Or either one, either one's fine. Maybe this is even easier, right? A plus 2 times 2 is 5, so a is 1, right? So we just figured out what a and b have to be so that this integral is the same as the one we started with. And so a has to be 1, and b has to be 2. And then now we've got the decomposed version of our original fraction, and we got an easy antiderivative, right? So we can just do, coming down here for the answer, my blank space here, antiderivative of 1 over 2x plus 1, natural log. Is that right? Not quite. Think about taking the derivative of that. What else would we need? We didn't need a half, right? Plus 2 times. So that is the antiderivative of the, since this rate function is equal to that rate function, this is the antiderivative of this, right? So that's the antiderivative of our original problem. Questions on this technique before we do some harder ones? So that was an easy one.
How many letters is it going to go up to?
3 the most. Yeah. Last chance. Questions on this one? Is there one question? Okay, ready? I'm going to take it out. All right, so let's try a more complicated one here. Sure. Come on in, learn some calc. Squared, okay. That's x squared. Okay, x squared plus 1 over x minus 3, x minus 2 quantity squared. So, do we have the requirement of n, the degree of the numerator, less than the denominator? Are we good there? Okay, and then do we have a factored denominator? Or we have the product of factors? Yes, we do. Okay, so with a little more complicated one like this, we have to consider all possible. So we want to rewrite x squared plus 1. We have to consider all possible denominators that, when added together, could make that common denominator. So we'll have x minus 3, and we'll have x minus 2. But we're also going to have something else. X minus 2 squared. Okay, well then you ask, well, why not, do we need x minus 2 times x minus 3? No, because that would be taken care of by these two added, right? So x minus 2 times x minus 3 is already kind of implied by adding these two. But just x minus 2 squared is not covered by just having 1x minus 3 or 1x minus 2. So it's another possible denominator we could have, such that the common denominator would be this one. Okay? So this is what it would be. All right, let's see if I can do it. Think of a fast example here. Because if I added 5/3 plus 7/2 plus 11/4, what would the common denominator be? Be 12, right? And so, how many twelfths is that? 20 plus 42 plus 33, which is 53, 75? Okay, there's no way to get 75 twelfths by just 95. I was just testing you. Okay, so there's no way to get 95 twelfths by doing something over 3 plus something over 2. It's impossible. You can't do it. You can't get 95 twelfths by doing something over 3 times something over 2. You also need something over 4 to get it. And that's the same idea as what's going on here. You have to also have something over 4 to get the fraction 95 twelfths. Without that c over 4, this is impossible. Can't do it. So who asked that? Does that kind of help?
Yeah.
So it's the same analogy that this is like one thing and another thing and then that other thing squared. And so we've got to have that term c over x minus 2 squared. That could see that there could potentially be a fraction that we need to get it to equal to this. Yeah.
So just to clarify, if it were a multiplicity of 3, it would have factors of x minus 2, or over x minus 2 plus c over x minus 2 squared, and then plus the x minus 2 cubed. All of them, because they're all...
If this was x minus 2 cubed?
Yeah.
Yeah, then you need x minus 2, you need x minus 2 squared, and you need x minus 2 cubed. That's right. That's right. Okay. Okay, so let's go. We'll work fast here. Okay, so what do we know? We know it's going to be, so a times what? Can we just go right to the numerator? A times what will give us this common denominator of x minus 3 times x minus 2 squared?
X minus 2 squared.
X minus 2 squared, I'm going to need times a. Do you see that? I need x minus 2 squared over x minus 2 squared. And then what will b be times?
X minus 3.
And so we've only got one x minus 2 down here. And this is x minus 3 and x minus 2 squared, so b will be x minus 3 times x minus 2. And then what about c? Just x minus 3. Again, we're thinking about, we're adding those fractions together, and what do we need to do to each one of them to get the common denominator? Well, the first one, I got to multiply top and bottom by x minus 2 squared. So that's why I have a times x minus 2 squared. The second one, I got to multiply top and bottom by an x minus 3 and an x minus 2 to get the common denominator. And the c, I got to multiply the top and bottom by just x minus 3, and that will give me the common denominator for that one. And so then all this together should equal x squared plus 1, right? Our whole numerator, when we do that, should be x squared plus 1. Okay, so now we're going to gather x squareds, we're going to gather x's, and we're going to gather the constant terms. So what about x squareds? We're going to have ax squared, and we're going to have a bx squared. I'm just going to do them by powers of x here. Any other x squares? No. And that has to equal 1x squared. All right, now powers x. So here we're going to have minus 4x. Do you see that? So a times minus 4x. Here we're going to have minus 5x. And then what do we have for c? We have just x, right? And then how many x's do we have? 0 x's. And then constant terms. What constant term do I have here? 4. 6. Minus 3. And those have to equal 1. So what equations do I get? I get a plus b equals 1 from the x squared. I get minus 4a minus 5b plus c equals 0 from the x's. And then I get positive 4a plus 6b minus 3c equals 1. Okay, so what I'm going to do here, so now I've got 3 equations, 3 variables. So you might use a matrix method, you might use elimination, substitution, combination thereof. So what I see here is I've got this equation a plus b equals 1. If I could eliminate c from these two, then I'd have another equation of a plus b, and I could combine it with the first one. So when I combine these second two, I want to eliminate c. So to do that, I'm going to multiply this equation times 3. Because what I foresee is that I'm going to have positive 3c and minus 3c. And those will add together to be 0, leaving me an equation of just a and b, which I can combine with this one like I did in the first example. So when I do that, what do I get? So this becomes negative 12a minus 15b plus 3c equals 0 still. And now I'm going to add these two equations. And I'm going to get minus 8a minus 9b equals 1. And I've got a plus b equals 1 from the one I haven't used yet, right? I haven't touched that one yet. And then what I got when I combine the second and third. And that's just an example just like the first one. So again, however I can solve that. So once I can get a and b from those two, then I can get c from any one of those, or either one of those, the first two. And I have a, b, and c. And then I would know exactly what my partial fraction decomposition was, and I can do the antiderivative. So just for time's sake, let's just, I've done this problem before, so let's look it up. So what we get is you can write down a equals 10. You can do this on your own time. Verify it. A equals 10, b equals negative 9, and c equals negative 5. And once you put those into our original, you put a, b, and c into that original integral, then you got 3 easy antiderivatives. You can do them. What's that?
You look at their numerators are always 1 degree less than the denominators. That negative 5.
Oh, yeah, we didn't talk about that yet. So we'll talk about that. So you'll have a few homework problems for Friday. What?
Would that be on like the web work?
I'll only give you web work that's consistent with what we've done today. Okay, so you have a few problems for Friday, and then we'll continue this conversation of Wednesday, and then we'll continue the conversation Wednesday.